Molecules exist in a number of shapes, including linear, planar, and tetrahedral. The shape of a molecule is determined by the strength of repulsion between pairs of electrons in molecular orbitals and non-bonding orbitals. This results in different molecules having different sized angles between their covalent bonds. In this lesson, you will learn how to predict the shape of a molecule and the angles between covalent bonds using the valence shell electron pair repulsion theory. The shapes of molecules can be explained and predicted using valence shell electron pair repulsion theory. The first rule of the theory is that pairs of electrons repel each other. We can explore this rule with the molecular compound methane, CH4. The top left box shows the central carbon atom and surrounding 4 hydrogen atoms in a molecule of methane. Notice the number of electrons in the outer electron shells and in the covalent bonds. Click Labels to see a covalent bond labeled. How many covalent bonds are in this molecule? Answer: 4. The bottom left box shows the shape of a methane molecule. Covalent bonds between the central carbon atom and the 4 hydrogen atoms point to the corners of a tetrahedron. Notice that this gives an angle of 109.5 degrees between any 2 of the bonds. How many faces has a tetrahedron? Answer: 4. Ideas about molecular orbitals and electron repulsion can be used to explain the shape of a methane molecule. The large box on the right shows the molecular orbitals. Move your cursor over the orbital diagram to rotate the molecule. Each of the carbon-hydrogen covalent bonds has a molecular orbital formed by the overlap of a sp3 hybridized orbital of the carbon atom and the 1s atomic orbital of a hydrogen atom. How many electrons are in each of the 4 molecular orbitals? Answer: 2. Each molecular orbital contains electrons that have negative charge. Negative charges repel each other. The 4 molecular orbitals each contain an equal quantity of negative charge and are identical in shape. Therefore, they have identical repulsion from each other. This pushes the 4 molecular orbitals as far apart as they can get, giving a tetrahedral shape to the molecule. Select 3D Model from the drop-down menu. The large box on the right shows the tetrahedral shape of a methane CH4 molecule. Move your cursor over the shape to rotate the molecule. Select Ball and Stick from the drop-down menu. Now the large box on the right shows the atoms in their correct 3-dimensional positions in the methane molecule. Move your cursor over the shape to rotate the molecule. The shape of a methane molecule cannot be the same as the 2-dimensional shape of the electron shells, as shown in the top left box. Why? Answer: repulsion between pairs of electrons pushes the orbitals into a different tetrahedral shape. The top left box shows the valence shell electrons in an ammonia molecule. NH3. How many covalent bonds are in this molecule? Answer 3. Click Labels to see a covalent bond labeled. The bottom left box shows the shape of an ammonia molecule. The large box on the right shows the 3 identical molecular orbitals in an ammonia molecule. Move your cursor over the orbital shape to rotate the molecule. These molecular orbitals form when atomic orbitals of nitrogen and hydrogen atoms overlap to form covalent bonds. From which atomic orbitals in the nitrogen and hydrogen atoms was each molecular orbital formed? Answer: 1s in hydrogen and 2p in nitrogen. The fourth orbital is a non-bonding orbital containing a lone pair of electrons. This exerts a greater repulsion than the molecular orbitals, slightly changing the shape of the molecule. Notice that the angle between the hydrogen covalent bonds in ammonia is 107 degrees. This is less than the 109.5 degrees between any two of the bonds in the methane molecule. Why is the angle less in ammonia than in methane? Answer: the lone pair electrons exerts a greater repulsion, pushing the molecular orbitals closer together. Select 3D model from the drop-down menu. The large box on the right shows the positions of the atoms and the non-bonding orbital in an ammonia NH3 molecule. The structure is based on a tetrahedron, but the 3 hydrogen atoms are pushed a little closer together than they are in methane. Move your cursor over the shape to rotate the molecule. Select Ball and Stick from the drop-down menu. Now the large box on the right shows the atoms in their correct 3-dimensional positions in the ammonia molecule. Move your cursor over the shape to rotate the molecule. The top left box shows the valence shell electrons in a molecule of water, H2O. The oxygen atom has 2 covalent bonds joining it to the hydrogen atoms. The oxygen atom also has 2 non-bonding pairs, lone pairs of electrons. Click Labels to see a covalent bond and the lone pair of electrons labeled. Therefore, the oxygen atom does not have a 3rd covalent bond joining it to a hydrogen atom, as the nitrogen atom does in ammonia. Why? Answer: a 3rd covalent bond would exceed the maximum number of electrons in the shell. Once 2 covalent bonds are formed, there are no spaces for more electrons to be added in the atomic orbitals of the oxygen. The bottom left box shows the 2-dimensional arrangement of atoms in a water molecule. Why are the 2 lone pairs not shown? Answer: lone pairs of electrons and orbitals are not shown in ball and stick models. Notice that the water molecule has an angle of 104.5 degrees between the 2 covalent bonds. This is less than the angle between the bonds in methane or ammonia. You will discover why on the next page. The large box on the right shows 2 molecular orbitals for the covalent bonds between oxygen and hydrogen, and 2 atomic orbitals containing the non-bonding electrons. Move your cursor over the orbital diagram to rotate the molecule. The idea that repulsion between pairs of electrons in different orbitals has different strength is an integral part of the valence shell electron pair repulsion theory. For the orbitals below, repulsion becomes weaker as you move down the list. Between lone pair electrons and lone pair electrons. Between lone pair electrons and bonding pair electrons. Between bonding pair electrons and bonding pair electrons. The greatest repulsion between pairs of electrons in the water molecule is between the 2 lone pair electrons, pushing the orbitals much further apart than a tetrahedral angle of 109.5 degrees. These 2 lone pair electrons also exert a powerful repulsion against the 2 bonding pair electrons, pushing them much closer than the angle in methane or ammonia. The smallest repulsion is between the 2 bonding pair electrons, and this is not enough to push them further apart than an angle of 104.5 degrees. Select 3D model from the drop-down menu. The large box on the right shows the tetrahedral shape of a water H2O molecule. Move your cursor over the shape to rotate the molecule. The shape is similar to a tetrahedron, but the lone pairs are further apart and the hydrogen atoms closer together. Select Ball and Stick from the drop-down menu. Now the large box on the right shows the atoms in their correct 3-dimensional positions in the water molecule. Move your cursor over the shape to rotate the molecule. The shape of a water molecule is a V shape. Notice that both ammonia and water have lone pair electrons. Why is the angle between the covalent bonds joining hydrogen atoms in water less than that in ammonia? Answer: lone pair repulsion is greater than lone pair bonding pair repulsion. Summary: the shape of a molecule can be explained and predicted using the valence shell electron pair repulsion theory. Repulsion between electron pairs results in the orbitals moving to a position as far apart from each other as possible. For the orbitals below, repulsion becomes weaker as you move down the list. Between lone pair electrons and lone pair electrons. Between lone pair electrons and bonding pair electrons. Between bonding pair electrons and bonding pair electrons.